Welcome to section 3.4, which is a really interesting section, and that is setting the stage for chapter 4. Chapter 4 will completely blow open the world of linear algebra in ways that we have not even scratched yet. 3.4 is very interesting in that sense. It shows us how we can use different bases to solve problems. So we're going to study how to define the standard basis as well as different bases in a linear space. We're going to learn how to write vectors in different bases. We're going to find the vector B of a linear transformation after having switched bases. And we're going to perform a change of basis to go from the matrix B we would have found to matrix A in the original basis. So, just a reminder, a basis is a set of vectors that are linearly independent and that span the space. And the number of vectors in a basis is a constant. You can choose the basis in infinitely many ways, but you will always have the same number of vectors in the basis. So, for example, for a basis of R3, it will always have 3 vectors, whether you choose the standard basis or any other. So if we consider a basis V1 Vm, which is maybe not the standard basis, any vector x in the subspace can be written uniquely. So there's one way to use those vectors to express a new vector. And C1, C2, C3, Cm are called the B components of the vector x. The vector like this is called the B-coordinate vector, and it is written like this. So we are talking about a vector x. If you looked at the image geometrically, it would not be different. It would be the same arrow that you see, but the components of that vector would change because we would be using a different set of basis vectors. Notice that I always put a B at the bottom right of a vector when it is expressed in a different system of basis vectors. This is a little bit different from our textbook. I felt that this was more kind of explicit on what is going on, but it does sometimes lead to ambiguities. When you see that, it means the vector that is expressed in the basis B. So why would we ever want to do that? Well, for example, here, even though this has no explanation on what the task would be, if we were looking at vectors that are pointing at every point on an ellipse, this could be difficult because this ellipse is tilted. If you try to think of what the parametric equation would be for that ellipse, I don't know what it would be. However, if we were able to switch the problem by now focusing on new vectors, let's say vector v1 like this and v2 like that, aligned with the principal axis of the ellipse, now I would be able to write parametric equations using this new basis, so using this new system of axes that is tilted in the same way as the ellipse. So, there's a lot going on in this image, and we're going to go step by step to see like all the layers are together in one image, but we're going to want to think about them step by step. First step is the x1 and x2 axis. So this is just the basis, the basic system of axes, x1, x2. This would have standard basis vectors e1 and e2. They are not shown here, but we could imagine e1 and e2 being here and there. We are wanting to choose 2 new vectors that would define a new basis for R2, for the plane. And we choose vectors v1 equals 3, 1, and v2 equals negative 1, 3. So this is vector 3, 1, 1, 2, 3, 1, and then v2 is negative 1, 1, 2, 3. So we are expressing v1 and v2 using the standard basis vectors e1 and e2. Now that we've defined a new basis, it's a reasonable choice because we have two of them and we're in the plane, so we need two, and they are clearly linearly independent. We could express any vector in the plane using v1 and v2 instead of using e1 and e2. And that's what we're going to do. We're going to try to express vector x here, which is the vector 10, 10. So it's 10, 10 because it's 10 times e1 plus 10 times e2. That's just a normal way we express vectors. But how can I express vector 10, 10 in basis b? The question is, how many times v1 is it, plus how many times v2 is it? And this is where this overlaid tilted grid comes, because we can see from that it's 4v1 plus 2v2. So the answer would be vector x in basis b is vector 4, 2. But how do we do that if we don't have geometry and if it's not easy to figure out what the components are? Well, we are wondering, vector 10, 10, how many times is it 3, 1 plus how many times negative 1, 3? So we have a small system of equations. 10 equals 3a minus b, and 10 equals 1a plus 3b. And if you solve that, you find a equals 4, b equals 2. So we write that vector x using basis b is 4, 2. And we should have a little b here just to be consistent. Oops. Well, let me see if I can do that. B. Second question. If we know that a certain vector y is the vector 2, negative 1, expressed in the vectors of basis b, so this is vector y here, it's 1, 2 v1s minus 1 v2. What are the components of this vector in the standard basis vectors, using the standard basis vectors? So how many e1? 1, 2, 3, 4, 5, 6 maybe, and minus 1. That's a rough guess. The way we do that is actually easier than question A. We're simply going to do 2 times v1 minus 1 times v2, and it'll immediately give us the answer. It's 7 e1s minus e2. So y expressed in the standard basis is 7, negative 1. That's the way I suppose everybody would solve this problem if I hadn't, if we were not going further. I'm sure everybody is able to do that. But there's an alternative method that we're going to study now, which is actually going to lead us to a really powerful kind of standardized way of solving this problem in linear algebra. And the first thing we do is we define a new matrix that we will call S. It will always be called S, and it is simply made column by column using the basis in our new, using the vectors in our new basis. So in this example, S would be 3, 1 and negative 1, 3. It's written right here. We can think about what this matrix does. Now, granted, this is a little bit counterintuitive, but what S does is it translates a given vector in basis B to the standard basis. Let's see an example to see how this is true. And somehow I find it a little counterintuitive because it feels to me like it's going backwards, but this is what it does. Indeed, if we chose vector 1, 0, if we just put 1, 0 here, and we proceeded to multiply S by 1, 0, we would get 3, 1. We would basically get the first column, right? So what this did is we took a vector that is defined in basis B, and it gives us the component in the standard basis. Likewise, if we take vector 0, 1, and it happens to be to make sense of what matrix S does, we have to realize, oh, this is 0, 1 in basis B. If we multiply, we get negative 1, 3, indeed, the second column. So it has transformed vector v2 expressed in basis B to V2 expressed in the standard basis. And now this means this is a very useful matrix, right? It's going to allow us to solve these questions. It's going to allow us to solve question B most easily, because that's what S does. It transforms something from basis B to standard basis. So let's do question B first. We have the vector 2, -1 in basis B. What is that in the standard basis? We just do S times vector 2, -1, and we get 7, -1. So that would be that same vector Y, but using E1, E2. If we want to solve question A, it's a little bit more work, because the setup is S times a certain vector X expressed in basis B is equal to 10, 10. So to solve that, we have to multiply by the inverse of S. So we have X in basis B equals S inverse times 10, 10. And maybe using a calculator, we would find 4, 2. This matrix S is going to come up a lot, and it's always S that is used. One key information is that everything we've defined until now in linear algebra about the standard basis is also true about any new basis we create. In particular, we can find the matrix that does a certain transformation by looking at each vector in the new basis and building the matrix B column by column. If you're not sure what I was saying here, we're going to see an example right away. So originally, when we were working only with the standard basis to construct the matrix of the transformation, we would simply look at the image of each standard basis vector, and for what we're studying now, it is the same. We simply look at the image of every basis vector in the new basis. So let T be a linear transformation that projects any vector orthogonally on a line spanned by the vector 3, 1. Find a convenient basis B for that transformation and write the B matrix of the transformation. So we have all vectors in the plane and we want to project them on this purple line here. This is something we did in section 2.2, and we were kind of provided a matrix to do that. We're going to see how we can actually do it ourselves with understanding every step of the way. So clearly, basis E1, E2 is not ideal for this problem. It is much wiser to choose a new basis, which would be made of V1 and V2 aligned with the projection. Because after that, V1 projected would remain on the line and the projection of V2 would become 0. So we choose to construct a new basis where our vectors are V1 and V2, which are 3, 1, because it's given here, and a vector perpendicular to 3, 1, so -1, 3. You could also choose 1, -3. To construct the B matrix, we need to look at what happens to V1 when it is transformed. So the vector 3, 1 is actually the vector 1, 0 in this new basis. And what happens to 1, 0 in this new basis? When it is projected, it remains exactly what it is. So 1, 0 goes to 1, 0. So this is the first column of matrix B. What about the second vector in our new basis? It's the vector -1, 3. So this corresponds to the vector 0, 1 in basis B. And when we project vector 0, 1, it becomes vector 0, 0. It's projected perpendicularly, and since it is perpendicular, it becomes 0, 0. So that becomes the second vector in matrix B. So matrix B is super easy. It's 1, 0, 0, 0. We're going to see in a minute further how the matrix of that linear transformation is. In this context, it's very easy to find B. So B is great, but we would really prefer to have the actual matrix of the transformation using the standard basis. So finding a different basis is going to be a really convenient step, but ideally we want to come back to the standard basis. So if we have a vector x in the standard basis, we would like to know what matrix A is that transforms that vector. You can imagine that this is a soccer player and they want to pass the ball to another soccer player in the same team, but somehow there's someone in the middle, so this is not possible. The way we're going to find matrix A is that we're going to kind of make a sidestep to here, and then we're going to transform using matrix B. We saw it's really easy, and then we're going to make a sidestep back. This is like passing the ball to a teammate who can then pass it forward, and then from there, again on the side, to the original plan. So what is going on here? These three steps that we're going to do are going to be exactly equivalent to using matrix A. They are going to be change from the standard basis to our new basis, then use matrix B, and we saw in the example earlier how easy that was, and then change back from the basis B to the standard basis. Okay, let's read the question. For the example above, so the projection on the line spanned by vector 3, 1, find the standard matrix A of T in the basis E1, E2, so in the standard basis. There's two ways we can do that. Number one is just using concept we saw in section 2.2. And number two, option 2, is to use this diagram and what I explained just now. So A, it's interesting to do that for two reasons. Firstly, to remember that we know how to make a projection. And two, in order to verify that our answer in question B is correct. So the formula, I wouldn't remember that by heart, but the formula for an orthogonal projection is given here. And that means that matrix A is 9 over 10, 3 over 10, 3 over 10, 1 over 10. All right, so this is what we did in chapter 2. But now we can also say that A is the same as going here, here, here. So the first step is changing from X to XB, which requires us to perform S inverse. And then we're going to perform B, and then we're going to perform S. So be careful, because when we will write matrices, we proceed from right to left. You have to imagine vector X is right here. So if I multiply by X, it's going to be S inverse times X first, and then it's going to be B times that, and then S times that. So even though we start with S inverse shows up at the end of this. So we can write SB S inverse like this. S is simply made of the new basis vectors. B, we found it in the previous question. And S inverse, we can calculate it. And if you do that, either by hand or on your calculator, you will see that we find indeed that A is 9 over 10, 3 over 10, 3 over 10, 1 over 10. So it's a wonderful way to find matrices that might be difficult. This example was about an orthogonal projection, and we happened to know a way. We had a formula, but there might be other linear transformations that were not provided in chapter 2, or simply situations in another dimension. Everything we saw in section 2.2 was about transformations in the plane. So if we now were to talk about transformation in 3 dimensions, we could not refer to section 2.2. So finally, just as a conclusion, A is S, B, S inverse, where S is defined as the matrix whose columns are the vectors in the new chosen basis. Thank you so much. Goodbye.